Alrighty, so hello everybody. In this video, we're going to be going through the 6 rules in MD solids and kind of helping you out with that. So I always really enjoy having the students go through the MD solids 6 rules. This is just found here in the animated learning tools tab. Then we're going to be clicking right here for shear and moment diagram 6 rules. So we can go ahead and continue. They have the instructions for us. And we're going to go ahead and begin with part 1. Now, as we go through this, you want to make sure that at the end of your progress, you do end up looking at your self-evaluation scorecard and getting a screenshot of that. But anyways, let's pop back to rule number 1. Now, rule number 1 states that for concentrated forces, they're going to cause a jump or a discontinuity in the shear diagram at the location of the force. So this is exactly as we were saying, how if we have a beam here, and then we end up having a force right here of, that was 5 kilonewtons. And then, what is this, 6 meters here? We have that guy at 6 meters, and then this is 2 meters here. We're gonna end up having this concentrated force of 11 kilonewtons. And then we're gonna also have a counter moment here, 52.0 kilonewtons times meters, and then we have this guy right here, 6 kilonewtons. Now, in terms of this, we're just looking at the shear diagram, right? So don't be getting thrown off by this moment. It's just the shear. So what we can end up doing is we can create our shear diagram here. And so what this is going to end up looking like, and basically what this is this is an X and Y graph, where in the Y-axis it's the shear strength, in the X-axis it's the distance that we've traveled, right? So like right here, for instance, that's going to be 6 meters in, and then right here is the actual end of our beam, right? And so what happens in our shear diagram is we start at 0, well, we're going to pop down to -5 here. So we can represent -5 as this. It's going to be a horizontal line, right? As the rule of the line states, if we have a concentrated force, then it's a horizontal line for our shear diagram. Then what's going to happen is there's going to be a jump down an additional 6, and then it's going to go right here, and then it's going to pop up 11. So this is -11 here. This is -5 at that point right there. And so if we end up looking at this on the computer screen, they ask whenever x is equal to 2. Well, 2 is right here, right? We've only got the 5 kilonewton force. So what I also like to tell the students is actually block this part of the beam, right? So that at 2 meters, everything to the right of it you don't see, and then just take the sum of the forces. Well, it's just a -5 kilonewton force, right? So we can put this in here, -5. And then whenever we go to 7, just go ahead and block this, take the sum of the forces, well, that adds up to -11, right? Because if we go 7 meters in, so 7 meters from here, 6, and then an additional meter, block everything to the right, you got -5 minus 6, which gives us -11, okay? So the other thing too, they are going to be showing you the shear and moment diagram, so you can be checking those out. Remember, if the shear diagram has horizontal lines, the moment diagram is going to be sloped based off of the rule of the lines. So let's go again here. Let's go through this example problem. So this example here, we have a 5 kilonewton force that's going to be going down. Then we have a positive 9 kilonewton force here. And then we have a -4 kilonewton force again as well. We also have that moment because this is a cantilever beam. Remember, the moment, we're not looking at that. It's not in our interest right now because we're just looking at the shear diagram. So once again, what we can do, x equals 3. So imagine 3 meters in, it's going to be right here. Don't look at anything to the right here, just look at all the forces that are happening to the left of the x equals 3. So you can see we just have that -5 kilonewton force there. And then whenever x is equal to 4.5, so we can travel 4, and then we're just past this halfway, right? Don't look at any of this over here to the right, look at everything to the left. -5 plus 9 is going to give us a +4. So we can go ahead and click check, and as you can see, this is our shear diagram here. It is the case where it goes down -5, jumps from 0 to -5, and then whenever we get to this point here, it's going to jump up 9, then it's going to go as a horizontal line, and then it's going to pop back down with that support force there. Just as we were talking about rule of the lines, you have a concentrated force, it's going to cause a horizontal line for your shear diagram, and then it's going to be a slope line for your moment. Let's go ahead and go through C here. It's going to be the same case, x equals 5, so right here at this point, don't look at anything to the right, just looking at the forces to the left, take the sum of the forces. That's going to be a +36 minus 34, which is going to give us 2 kilonewtons there. whenever x is equal to 9, well, we're going to go 4 plus 4, that's 8, and then we go 1 more meter. That's going to basically be 2 minus 40, right? Now, how did I get the 2? Because positive 36 minus 34 is going to give us the positive 2. Then take that positive 2 minus 40, you get negative 38. So we got negative 38 there. We can go ahead and click check, and make sure you guys are looking at these shear and moment diagrams, right? Be thinking about that as well as you're going through this, what those are going to end up looking like. So let's go ahead and go with D here. It's the last one. So whenever x is equal to 10, so we're going to be somewhere around here, right? We're going to be 4 meters past this because 6 plus 4 equals 10. So in this case, it's going to be that positive 18 minus 38. That's going to give us a negative 20. And then if we go 14 meters in, it's going to be 12, and then plus an additional 2 here. So we can go 18 minus 38, negative 20. Plus 24 is going to give us a positive 4. Now, this is the trick that you can always use. If it's right here in this section between this last applied force and the support force, it's actually going to be equal to whatever the support force is, as you can see here. So that ends up popping up, and then we have to end at 0 here, right? So then that's how we know that this point right here was 4 kilonewtons, because this is a negative 4 kilonewtons there. Anyways, that is rule number 1. We can go ahead and move on to rule number 2. So rule number 2. Now, what rule number 2 states is the change in shear force between any two locations is equal to the area under the distributed load curve. And so we've got currently, what is this, 11 meters is how long our beam is. I'm going to set this up as a scale this time around. 2, 4, 6, 8, 10, and then 11. So each of these little grids is going to represent 2 meters for me. Now we have this occurring for 6 meters. 1, 2, 3. So we got this guy, this is the uniformly distributed load, right? And then what they're basically saying is if you treat this as a rectangle, right, where the 5 kilonewtons is actually the height, right, because it's the magnitude, and then the x, or the base, is 6 meters, right, which is what we know, it's 6 meters here, then what they say, that shear diagram, or that area underneath this uniformly distributed load is going to be what that shear force is, or the change in shear force. So let's go ahead and let's just create the free body diagram here. We got 30 kilonewtons here, and then we've got a counter moment as well, 240, our reaction moment, kilonewtons times meters. This is 5 meters here. Okay, perfect. So they're saying whenever x is equal to 2. So what we can actually do is we can describe our shear force as an equation. Now in this case, there's no reaction force here. So what we're going to end up having is this going to be negative 5 times x, and that's going to be up until we get to the 6 meter mark, right? Because in this case, it only lasts for the 6 meters. So we could say where x is less than or equal to 6, and then we should also say that that's 0 less than or equal to 0 as well. So we can end up using this equation right here. So if we end up going through here, well, they say if x is 1.5, well, plug that in. X is 1.5 times negative 5, that's going to end up giving us a negative 7.5, right? Now, what is the equation for the area of a rectangle? Imagine this, 5 right here, right? And then this is just the case where I have this being equal to x. X is just down here. So now we can plug in whatever we've got for x. So just in that case, right, we said plug in negative 1.5. And so that's how we got 1.5 times negative 5 gives us negative 7.5. So now they say, well, what about whenever x becomes 4? Well, if x becomes 4, go ahead and plug that in. That's going to be negative 20, right? So it's going to be right here at this point. So we can put in negative 20. And then we can check this. Now this is where it starts to get pretty cool in terms of this line that you can see on my computer screen right here, right? That line is actually going to be modeled using this equation right here. So notice that this is the slope. And so we start at 0, and then just as we said, whenever x is 1.5, so if I go in here, 1.5, that's gonna be equal to that negative 7.5. And then whenever x is 4, it's gonna be equal to that negative 20. So we can kind of try to, I guess we could have set up a scale there too. But this equation right here, you can think of as y equals negative 5x. And then we don't have a y-intercept, right? There's no b because just 0. But anyways, then what ends up happening, because there's no uniformly distributed load applied here, it ends up, so this is going to end at about negative 30. It's going to continue here, and then we go up that positive 30. So this is negative 30 here is what that centers out at. But anyways, that's what that shear force diagram looks like. So we can go ahead and continue with these. In this example, I'll go 2. So this is 2b here, right? We have this now where it's going to be the case, excuse me, where we're going to have 2 rectangles, right, that we're going to be calculating the area. If we end up going past this 6, that's whenever we're going to have to start taking into consideration the area of this guy as well. And so if x is equal to 4, in this case, just imagine we've got a rectangle right here, which is 6 as the unit, and then we've got it where this guy right here is 4. So if you take 6 times 4, right, we're going to end up with 24. That is going to be a negative 24 because it is pushing downwards with our uniformly distributed load. Now, whenever we get to x equals 13, it's going to look something like this. So we've got that 6 right here, right, and I'll try to use a bigger scale here for this. So 6, and then it's going to go by 6, which is just a square, right? So 6 by 6. And then we move up to 12. So then we've got this 12 by 14. Well, guess what? We're only going 13 meters in. So if you take 13 minus 6, right, that's going to end up giving us 7. So it's going to look something like this. So 7, and then this is 12 right here. So then what we can do now is find the area of these two. Well, this is 36, right? And then 7 times 12 is going to end up giving us 84. If we take 84 plus 36, we're going to end up with 120 for our shear force there. So that's a negative 120 there, negative 120. All right, and now whenever you look at this, you can see our diagram. So remember, horizontal line, it's going to cause a slope line for your shear. And then it's also going to end up causing a curved line for our moment diagram. And remember, if we actually find the area of this guy, then we can end up finding out what the max moment is going to end up being, or sorry, not the max moment, but just what the moment is going to be at this point. So if we take the area of this triangle, that's going to be 108 there. All right, so let's go ahead and let's go to C. In this case here, we've just got, okay, so this is where they switch it up on us a little bit. Let's go to C here. So 2C, it's the case where we actually have a positive 32 kilonewtons. So let's create the free body diagram here first. So we've got 12 by 6. That's going to be a total of 18. I'm going to go that 2, 4, 6, 8, 10, 12, 14, 16, 18. So we got a scale here. Now we're going to have 32 kilonewtons that we're starting off with, and then this is going to be the uniformly distributed load that's going to last 1, 2, 3, 4, 5, 6. That's going to be 12 meters in. Okay, and then this is 4 kilonewtons per meter. So remember, this is like the height of this as a rectangle, and then we've got this last for 12 meters, and so per meter we're getting 4 kilonewtons of force. And then this guy right here is 6 meters, and so now we've got a 16 kilonewton force here. So now what we can do is we can represent this also as an equation. If we look back on this, this is V equals, well, you have a positive 32, right? And then we've got a minus 4 times X. Now this is where X must be less than or equal to 0, but then greater than or equal to, let's hear it. Did I switch this around? No. Yeah. X must be greater. Yeah. Okay. X must be greater than or equal to 0. Gosh, I'm too early in the morning. Haven't had enough of the coffee, clearly. X must be greater than or equal to 0, but then also less than or equal to 12 in this case for this. So now we can end up using this equation to model this out. And basically this is going to be the line for our shear diagram for that first part there. So we've got that. And so we can use this equation to determine this. So for this guy, we have 1 meter here, right? Well, plug this in to 1, right? We've got positive 32 minus 4 times 1, right? It's just going to be minus 4. So that's going to be 28. Now this is in terms of how you can think of this in terms of the algebra, right? In terms of just the basics here, if you have a positive 32 kilonewton force, if we're going 1 meter out, well, this applies 4 kilonewtons per meter, right? So then of course that's gonna be 4 kilonewtons down. So then it's just a process of taking 32 minus 4, right? So we got 28, that's gonna be positive. And then in terms of once we go 10 meters in, it is gonna be the case where we start at 32, then we can go minus 4 times 10. Well, it's 32 minus 4. We're gonna end up with a negative 8 there, right? Now, how can we think of this in terms of our rectangle? If this is 4, remember, you can plug in this as being 10 here. That gives you 40, and that's downward, so this is negative 40, and then you have that 32 there going up, so 32 minus 40 gives us that negative 8. And so whenever we go to click check me, you can see this, and this is our equation right here, right? This is the equation of the line. Do you guys remember in algebra learning y equals mx plus b? Well, isn't that what this form is? Instead of being y, it's v, right? Because we're plotting out v in the y-axis, equals negative 4x. So what's your slope? Negative 4. And then we've got plus 32 because that's where it's the y-intercept. As you can see, it's going to intercept the y-axis right there at 32. And so that's how we end up getting that. Remember, we can also take the moment, or not the moment, we can get the moment from taking the area of this right angle triangle here. And so that will give us 128. But anyways, let's go ahead and move on to D. In this problem here, we've got a negative 7 kilonewton force. Now this is where we've got to be kind of careful though. This uniformly distributed load is not actually acting until 4 meters in. Okay, so be careful with that. We got to keep that in mind. So whenever x is equal to 6 meters, when x is equal to 6 meters, what is our shear strength? So let me get another piece of paper here so we can draw this guy out. It is going to be the case for 2D here that we've got this beam. Let's go ahead and set up our scale. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We're going to go in 4 here. So this is where this force is acting. Oh, and sorry. So we can put this as negative 7. Let's do that, negative 7.1 kilonewtons. Remember, that's just meaning that it's going the opposite way. And so this is 4 meters here. And then this guy is going to be occurring for the 10 meters. And I'll put this guy as the actual 12.9 kilonewtons. And then, so now we've got this uniformly distributed load that's being applied upwards now in this scenario. And as you can see, this kind of switches things up for us here. So this is 2 kilonewtons per meter. Remember, that's a magnitude there. And so now we've actually got these downward forces here for our reaction supports. And so now whenever we go through this, well, if this first 4 meters, we're not applying any uniformly distributed load, it's going to be the case where our shear diagram is going to be starting off at a negative 7.1, right? So what's going to be the case up until the 4. Now at this point, that's whenever we're going to start taking on the line, right? And so what's going to happen is this guy's going to start moving up with a slope of 2x there. And so what we can do is we can determine whenever x is equal to 6 meters, what ends up happening. Now, in terms of this guy, we do have this where it's starting off at 4, so we're 2 meters into here. Well, if we end up finding our triangle here, it's 2, and then we're going 2 meters in here, right? So it's 4 is what we end up getting for that. And then if you minus that 7.1 kilonewton force that's already acting in here, we get 4 kilonewtons minus 7 kilonewtons. And so what we're going to end up having, or 7.1 kilonewtons that is, we're going to end up having the negative 3.1. So we can go negative 3.1 there. And so remember, this is negative 7.1 here, and this is starting to move upwards, right? And so now we can also test this out whenever x is equal to 13. So it's the case, well, we're going to have 13, right? This is only acting 4 meters in, so take 13 minus 4, you get 9. So that's going to be the case where this is a rectangle, a 2 by 9, right? So 2, 4, 6, 8, 9. It's gonna look something like that. So 2 times 9 gives us 18. That's gonna be a positive 18 kilonewtons, and then minus that 7.1 kilonewton reaction force, right? That's happening here. It's going downwards, actually is what the case is. So then now we got 18 minus our 7.1. We're gonna end up with 10.9 there. So it's gonna be that positive 10.9. And so now as we go in and check this, you can end up seeing what these values are. Now, just as we were saying, well, what is this equation here? It is going to be a slope of 2x, right? And then you can see the y-intercept, or sorry, there's not gonna be the y-intercept there because this is just the end of the graph. But the slope of this is matching the slope of this guy here, all right? Let's go ahead, let's go to the next scene. So this is rule 3. So rule 3, and this is kind of what we were talking about just now. The slope of the shear diagram at any location is equal to the distributed load value, both the magnitude and sign at that location. So in this case, we've got, this is equal to negative 8 kilonewtons per meter, right? What we can do is we can start to express this as an equation of a line, right, for V. So V is going to be equal to, in this case here, it's going to be a slope line, right, because we have the horizontal line. The shear diagram is going to be a sloped line. V is equal to negative 8 times X, right, whatever X is, where X must be less than or greater than or equal to 0 or less than or equal to 12 meters, right? So we've got this plus that 54.9 kilonewtons. Now, just as we were saying, if this is the equation of a line, y equals mx plus b, it's going to be the case where this is our b, our y-intercept, this is the slope right here, right? And then this is the value of x that we can plug in to find out. Now, in these questions, what they're asking you, well, if v is equal to 0, where is x going to be, right? So now, or what is x going to be? If we plug in 0 for v, as you can see, we have one unknown, which is x. So can we solve for x? Absolutely. 8x equals 54.9. And so this is the point where this uniformly distributed load is going to finally cancel out our support load here. And so if we take this, we could divide by 8, right? Both sides. X is going to be equal to 54.9 divided by 8. And so we end up with a 6.8625 meters. And so that tells us 6.8625 meters in, V is going to be equal to 0. So if we go ahead and plug this in, we'll actually end up being able to even see the slope as well as the equation of that line there. And then once again, if you want to find out what this moment is here, you can take this area of this guy, right? If you take the area of this right angle triangle, you're going to end up getting 188.08. But that's how we can solve for these. We can go ahead and move on to 3B here. Now 3B, this is where we got to be careful. It is the case where 6 meters in, we do not have this uniformly distributed load being applied. And so what we need to do is we need to add 6 to X in the end, right, is what we can end up doing. So if we end up doing that, we can set this up. So V is equal to, now this is going to be the case where we're going to have a negative 14.2 kilonewton force, right? And then this is going to be plus, because it's going positive, it's going to be plus 4x there, okay? So now they're asking where V is equal to 0. We can end up setting V equal to 0 here, negative 14.2 plus 4x. Now we can set 4x equal to 14.2, right? Divide this by 4, divide this by 4. Now we're left with x equals 14.2, oops, sorry, I'm getting ahead of myself. 14.2 divided by 4, that's going to end up being 3.55 meters. Now, just as we were saying, though, we need to add x, or add 6 to the end, so plus 6 meters. Now we're going to end up getting that value of 9.55 meters, and so that's whenever V is equal to 0. So we can go ahead and do that, 9.55, just like that, okay? Sweet. So moving on to 3C here. We've got this equation again. Remember, we want to add 3 at the end here to X at the end of this, right? So once we solve for X, we're gonna add 3. Now this is the case where we have V is equal to, and here we have a positive 68.8 minus a 44, and then we go minus 7x. And so now we can end up solving for this. If V is equal to 0, we've got 68.8 minus 44. That's going to give us 24.8 minus 7x. Solve for x here. So then divide both sides by 7. X is then equal to 3.543 meters plus 3 meters, right? Because we said we got to add 3 to the end. So that's going to end up giving 6.543 meters. And so that's where V is going to be equal to 0. So we can go ahead and punch this in, 6.543. There you go. And so this is what that diagram looks like. Remember, it is the case there's no horizontal line here for our load diagram, so this is horizontal line here because we start with the concentrated forces. Once we get to that point of the horizontal line for the uniformly distributed load, though, it does become a line there. All right, so let's go ahead and, oops, did we just end up pressing replay? Let's go to D here, so we're going to go to 3B. We're going to go ahead and do this. So now we've got it. In this case, we've got this positive 32, so V equals positive 32 kilonewton force. Remember, this guy is going downwards, so this is going to be negative 6x. We want to also take into consideration, we want to add 3 to x at the end. All right, so add 3 to x at the end, and we're going to go ahead and solve this guy out. So we're going to go ahead and solve for V is equal to 0. We've got 32 minus 6x. We can now solve 6x, 32, divide by 6, divide by 6. X equals 32 divided by 6. That's going to end up giving us 5.33. Repeating, right? Meters plus we want to add on that 3 meters, because the reason why we're adding on that 3 meters again, guys, remember, is because this uniformly distributed load does not actually start until 3 meters in there. So 5.33 plus 3, it's going to end up giving us 8.33, and we can end up rounding that to 3 here. We can go 3 decimal places out for these 3's. So 8.333 meters in. So if we go ahead and do this, 8.333, we can check it. And as you can see, that's where V is equal to 0 on this graph. But anyways, hope that was helpful. At the end of this video, do make sure that you do get a screenshot of your self-evaluation scorecard here. So you'll want to end up getting that. Anyways, hope this video was helpful. Happy MD soliding. Catch y'all in the next video. Bye-bye.